Hello, everyone. Myself is Dinesh, and my roll number is 536, and my topic is algorithm behind modern storage systems, different uses for read optimized B trees and write optimized LSM trees. An algorithm is a set of instructions for solving a problem or accomplishing a task. The amounts of data processed by applications are constantly growing. With this growth, scaling storage becomes more challenging. Every database has its own trade-offs. Every application is different in terms of read or write workload balance, consistency requirements, latencies, and access patterns. B-trees. B-trees are a popular read optimized indexing data structure and generalization of binary tree. They come in many variations and are used in many databases, including MySQL, InnoDB, and PostgreSQL, and even file systems. HFS plus H3s in ext4. The B in B3 stand for Bayer, the author of the original data structure of Boeing. In a binary tree, every node has two children referred as a left child and right child. Left and right subtrees hold the keys that are less than and greater than the current node key, respectively. To, to keep the tree depth to a minimum, a binary tree has to be balanced. When randomly ordered keys are being added to a tree, it is natural that one side of tree will eventually get deeper than the other. One way to rebalance a binary tree is to use so-called rotation. Rearrange nodes, pushing the parent node of the longer subtree below its child and pulling this child up, effectively placing in its parent's position. B-trees allow for storing more than two pointers per node and work well with block devices by matching the node size to the page size. B-trees have the following properties. Sorted. This allows sequential scans and simplifies lookups. Self-balancing. There is no need to balance the tree during insertion and deletion. When a B-tree node is full, it is split into two, and when the occupancy of the neighboring nodes falls below a certain threshold, the nodes are merged. This also means that leaves are equally distant from the root and can be located using the same amount of steps during lookup. Guarantee of logarithmic lookup time. This makes B-trees a good choice for database indexes where lookup times are important. Mutable, inserts, updates, and deletes. Also, subsequent splits and mergers are performed on disk in place. To make in place updates possible, a certain amount of space overhead is required. A B-tree can be organized as a clustered index, where actual data is stored on the leaf nodes or as a heap file with a unclustered B-tree index. B-trees are characterized in the following: branching factor, the number n of pointers to child nodes, along with pointers, root and internal nodes hold up to n minus 1 keys. Occupancy, how many pointers to child items the node is currently holding out of maximum available. For example, if the tree branching factor is n and the node is currently looking at n by 2 pointers, occupancy is 50%. Height, the number of B-tree levels signifying how many pointers have to be followed during lookup. Every non-leaf node in the tree holds up to 9 n keys entries, separating the tree into n plus 1 subtrees that can be located by following a corresponding pointer. Pointer I from a entry ki points to a subtree in which all the index entries are such that ki minus 1 less than or equal to k search less than ki, where k is set of keys. The first and last pointers are special cases, pointing to subtrees in which all entries are less than or equal to k naught in the case of leftmost child or greater than k n minus 1 in case of rightmost child. A leaf node may also hold a pointer to the previous and next nodes on the same level, forming a doubly linked list of sibling nodes. Keys in all nodes are always sorted. When performing insertion, the first step is to locate the target leaf. For that, the aforementioned search algorithm is used. After the target is located, key and value are appended to it. If the leaf does not have enough free space, this situation is called overflow and leaf has to be split into two. This is done by allocating the new leaf, moving half the elements to it, and appending the pointer to its newly allocated leaf to the parent. If the parent doesn't have free space either, a split is performed on the parent level as well. The operation continues until the root is reached. When the root overflows, its contents are split between the newly allocated nodes and the root node itself is overwritten in order to avoid relocation. This also implies that the tree and its side always grows by splitting the root node. LSM-trees. The log structure merge tree is an immutable disk resident right optimized data structure. It is more useful in systems where writes are more frequent than lookups than that retrieval records. LSM trees have been getting more attention because they can eliminate random insertion, updates, and deletions. And figure 5 shows that structure of LSM tree, a memory resident table used for writes. Whenever the memory table is large enough, its outer contents are written on disk. Reads are served, hitting both disk and memory resident tables, requiring a merge process to reconquer the data. Many modern LSM-tree implementations, such as RockDB and Apache Cassandra, implement disk resident tables as SS tables, sorted string tables, because of their simplicity, easy to write, search, and read, and merge properties during the merge. Source SS table scans and merge result writes a sequential. As an SS table is a disk resident uh, order immutable data structure. Structurally, an SS table is split into two parts: data and index blocks, as shown in Figure 6. A data block consists of sequentially written unique key value pairs ordered by key. An index block contains keys mapped to data block pointers, pointing to where the actual record is located. An index is often implemented using a format optimized for quick searches, such as B-tree, or using a hash table for a point query. Every value item in a SS table has timestamp associated with it. This specifies the right time for inserts and updates, which is often indistinguishable, and removal time for deletes. SS tables have some nice properties. Point query, that is finding a value by key, can be done quickly by looking up in the primary index. Scans, that is iterating over all key value pairs in a specified key range, can be efficiently simply by reading key or value pairs sequentially from the data block. An SS table represents a snapshot of all database operations over a period of time. As the SS table is created by a flush process from the memory resident table that served as a buffer for operations against the database state for this period, retrieving data requires searching all SS tables on disk, checking the memory resident tables, and merging their contents before returning the result. The merge step during the read is required since the searched data can reside in multiple SS tables. The merge step is also necessary to ensure that the deletes and updates work. Deletes in an LSM tree insert placeholders, often called tombstones, specifying which key was marked for deletion. Similarly, an update is just a record with a later timestamp. During the read, the records that get shadowed by deletes are skipped and not returned to the client. A similar thing happens with the updates. Out of two records with the same key, only with one with later timestamp is returned. Since SS tables are immutable, they are written sequentially and hold no reserved empty space for in-place modifications. This means insert, update, or delete operation would require rewriting the whole file. All operations modifying the database state are batched in memory resident table. To reduce the number of IO operations and make them sequential, both B-trees and LSM-trees batch operations in memory before making an actual update. This means that data integrity is not guaranteed during failure scenarios, and atomicity, applying a series of changes atomically, as if they were a single operation, or not applying them at all. And durability, ensuring that in the face of a process crash or power loss, data has reached persistent storage properties are not ensured. To solve that problem, most modern storage systems employ WAL, write ahead logging. In B-trees, using WAL can be understood as writing changes to data files only after they have been logged. In LSM trees, WAL is used to persist changes that have reached the mem tables but have not yet been fully flushed on disk. In B-trees, difference between B-trees and LSM trees, they are mutable. In B-trees they are mutable. They are read optimized. And B-trees writes might trigger a cascade of node splits, making some write operations more expensive. Concurrent access requires read or write isolation and involves chains of locks and latches. In LSM-trees, they are immutable, they are write optimized. Reads might require accessing data from multiple sources, since data for the same key written during different times might land in different LAN data files. Maintenance or compaction is required, as buffer writes are flushed on disk. Thank you.